how do we find the value of the equilibrium constant? Well, the most direct way is to have a chemical reaction at equilibrium and measure the concentrations of the reactants and the products at equilibrium. So here we have H2 plus I2 gives us 2 high, and suppose that at equilibrium, the concentration of H2 is 0.11 molar, concentration of I2 is 0.11 molar, and the concentration of high is 0.78 molar. At equilibrium, and they're telling us that the temperature is 445 degrees Celsius. Do we need to know the temperature? No, we don't. Calculate Kc. Well, first we write the expression, the equation for Kc. So that's what we've been doing. So Kc equals high squared divided by H2 times I2. So this one's squared because of that coefficient. These have coefficients of 1, so they have understood exponents of 1. There we have our equation. We take the numbers, we put them in. So Hi is 0.78, and that's going to be squared. I'm going to divide by H2 and I2. Why did I leave out the units? Because officially what this is 0.11 molar per 1 molar. This is a reference value. These are all ratios, and so the units cancel out. And you can view that as a cool idea or, kind of a cheater shortcut thing or something, but it is what it is. Okay, so then we do the math. And so we've got dividing by two numbers multiplied, and this is fraught with peril. People do this wrong so many times. So there's 3 ways to do this. Okay, the way I do this is I do 0.78 squared, I divide by this, I divide by that. It doesn't make sense to most students. So fine. They want to multiply these because they're multiplied. Okay, you can do that. But you have to put parentheses around them if you're going to multiply. If you don't, you're going to end up with 0.78 squared divided by 0.11 times 0.11. Is that the same? Nope. No, it's not. So what happens is students will do the hard part. They'll get all the equations and the math right. They've got it set up right, and then they miscommunicate with the calculator, right? It's like, dang, it was the last thing that messed you up. So you can do this. Another thing, I really love this about the HP 36X Pro, not the HP TI. Sorry, I was talking about that the other day. It has this little fraction button. Other calculators have this as well. If you push this button on your calculator, it's going to give you a fraction. And so you can type in 0.78 squared, and down here you can put 0.11 times 0.11, and it understands what you mean. No parentheses, no extra thinking. Okay? So I just want you to be aware of this issue so that it doesn't mess you up. Okay, so choose the method that makes the most sense to you, and let's do the math. And what do we get? 50.3. So my calculator is saying 50.2 0.28099,174. So we don't want to just round that off to 50 and not write anything else down. Here we've got two significant figures in all of our concentrations. This is pretty typical for what we're going to see in Chem 1B. But when you do the math, write down at least 2 extra digits in case you need to come back and use this for another calculation. Because if we round everything at every step, we'll end up with wrong answers due to rounding errors. And so then I'm going to say, okay, well, that is 50. No units, right? Because these guys had no units. So unlike the rate constants where we had all kinds of different possible crazy units, right? Here, if we were using molarities, we would have different units depending on the equation. You could end up with them canceling out, but you could also end up with molarity cubed or all kinds of other things. But because we chose to do this reference thing, we'll have no units here. Any questions? Okay, so let's talk through this table because it helps us to understand what the equilibrium constant is really doing. So the equilibrium constant, as its name suggests, is a constant. It's going to be the same regardless of what the initial concentrations were. So we have multiple examples here. So here, the initial concentration, we've got some of the reactants, none of the products. At equilibrium, this is what we end up with. You take these numbers, we calculate, we get 50. In this one, we started with no reactants and only products. This is what we measure at equilibrium. We do the calculation, we get 50. Here we're going to start with equal amounts of all 3. This is what we get at equilibrium, 50. Here, this is like the first one, but we've doubled the H2 in comparison to the I2. This is what we get at equilibrium, still 50. Doesn't that seem crazy? What I'm in awe of are the people that figured out that if we put those concentrations together like this, that all of this works out like that. I mean, that's pretty sweet. Any questions? So the equation, the reaction comes to equilibrium from wherever it started. At equilibrium, the concentrations plugged into the equilibrium expression will give us the same constant. Okay, so we can calculate the equilibrium constant if we know the equilibrium concentrations. We can also do this if we know the initial concentrations and one of the equilibrium concentrations. Measuring the equilibrium concentrations of all the things can be difficult, if not impossible. So this is much easier because we can know the initial concentrations because that's what we put in there. We made that happen. We let it go to equilibrium, and we just need to get one of the equilibrium concentrations. How do we do this? Well, we can figure out or deduce the equilibrium concentrations from the stoichiometry. So here we'll start with a very simple reaction. A in the gas state is going to 2B in the gas state. So let's say we start out with 1 mole per liter of A and no B. And then at equilibrium, we measure and we find that this concentration is 0.75 now. So this is our initial concentration, this is the equilibrium concentration. We don't know the other one. Well, what's the change from initial to equilibrium for A? it went down negative, so negative because it decreased 0.25. So if I take the initial and combine it with the change, I get the equilibrium. Make sense? So if this went down by 0.25, how is B changing? It's going up, right? So it's going to be positive. Is it going to be 0.25? No, it's going to be 2 times 0.25, right? For every one of these, we make 2 of those. So if I lose 0.25 moles per liter of that, I'm going to gain 2 times 0.25 liters of the other thing. You see that? Anybody not quite clear yet? Because we're going to be doing stuff like this a lot. And so we need to really see that, yeah, okay, I see what's going on here. Because it's not going to get simpler after this, right? So it started at 0. We're adding 2 times 0.25. So the equilibrium concentration is 0.5. Everybody okay with that? It's, a twist on stoichiometry from Kim Monet. Okay. So the reaction shown between carbon monoxide and hydrogen is carried out with initial concentrations of CO being 0.27 and H2 being 0.49. At equilibrium, the product concentration is 0.11. Find the equilibrium constant. So we're going to make a table. And we can use the chemical equation as the header for our table. So we're going to separate each of the reactants and products. And if it helps you, you can put a double line there. And we're going to do the initial concentration, the change in concentration, and the equilibrium concentration. So guess what these tables are called? Ice tables. Ice. Right? Initial, change, equilibrium. Nobody wants to write those whole words out. Right? So we're going to take the information that we've been given and put it into our table. It says the initial concentration of CO is 0.27 molar. Okay, so 0.27 molar. And H2 is 0.49 molar. It doesn't say anything about what the concentration of the CH3OH is. What can we assume? You know what assuming does, but we have to do that sometimes. That there's none, right? So we're starting with 0 of this. Is that a reasonable thing to assume? Well, sure, that's what you're making. You're not going to start out by putting some of that in there. I mean, you can do that, but why would you, right? If this wasn't 0, they would have to tell you what it is. So they're not going to tell, if they don't say anything about the products, it's 0. Okay, so that's the initial. And then at equilibrium, they're saying the concentration of that guy is 0.11. They want the equilibrium constant. What we need to find the equilibrium constant is all the equilibrium concentrations. So we've got information about initial concentrations for everybody. And we have an equilibrium concentration for 1. So this one that we have the equilibrium concentration for, we're going to look and we're going to see, well, what's the change? Well, it went from 0 to 0.11, so we must be adding 0.11. Right? 0 plus 0.11 equals 0.11. So if this went up by 0.11, how did the CO change? It went down by 0.11. The coefficients here are the same, right? So if this one changes by 1, that one changes in the opposite direction by 1. So this one is negative 0.11. So we could do that math and we get 0.16 molar. Here, it takes 2 moles of hydrogen for every 1 mole of this guy. So this change is going to be 2 times the change that the guys with the coefficients of 1 had. So this is negative 2 times 0.11. 0.22, so this would be 0.27. If you like doing math in your head, go ahead and do that, but I recommend, if you're being graded on it, to check it with the calculator. Okay, so any questions about that? That's the new part that we're just learning. We write the equilibrium constant expression for the chemical equation. And you should always write this out. Don't just stick numbers in, but put the chemical symbols in there. Right? So CH3OH, coefficient of 1, so exponent of 1. Down here we've got the concentration of CO, again, coefficient of 1. Here we have H2, and that one's going to be squared because the coefficient is 2. Now we put the numbers in, but we're going to drop the units. So we've got 0.1 in the numerator, and we've got 0.16 and 0.27 squared in the denominator. Now I talked about 3 different methods that you can get the right answer out of your calculator. So use whichever one works best for you, and let's see if we can all come up with the same answer. At 9.4307? Yeah? Okay. An interesting thing that we've kind of been noticing is that even students that were really, really great in their math classes, and they can, they can do integrals and they can rearrange equations all day long, tie your head in knots. They may or may not know how to communicate that to a calculator. They may or may not know how to apply the math to an actual practical problem, right? So those are like 2 different skills. So you could be really good at math and have trouble applying it. You could be good at applying it and then have trouble simplifying it or whatever, right? So there's 2 places that can mess you up. How should we express this as our final answer? How many sig figs? 2. 9.4. So things get a little, or can get a little messy in here because there's subtracting and adding involved. And when you do that, sometimes you gain or lose sig figs. We're not going to get too hung up on stuff like that. So we're going to call this 9.4. There will be no questions on the exam that are asking you how many sig figs that should have or are making you choose between 9.43 and 9.4 and 9. Not going to do that. Okay. 9.4. Let's do another one. Reaction shown is carried out with an initial concentration of CH4, 0.087 molar. At equilibrium, H2 is 0.012 molar. Find the equilibrium constant. So we're going to make an ice table. We're going to let our chemical equation be the header for our table. And we're going to have 3 rows. I, C, and E. Initial, change, and equilibrium. Well, they told us the initial concentration of CH4 is 0.087. What are the other initial concentrations? 0. Yeah. They don't specifically say it, but it's the only reasonable thing. They give us one equilibrium concentration, and that's for the H2. So that's down over here, 0.012 molar. So I'm taking the words here, and I'm pulling out the numbers, and I'm organizing them in a table that's going to help me know what math to do. So for H2, we know initial and final, so we can calculate the change. 0 plus 0.12 is going to give us that final. Right? So, you could also think of this as being, like the addition line, right? So we're adding these two things to get what's down here. Okay, so if this went up by 0.012, how did this go up? This is 3 of those, right? And only 1 of these. So we could divide this by 3, right? But that can kind of get confusing. So let's think about this way. That is equal to plus 3x. So this one goes up 3 x's. This one's going to go up 1x. And this one's going to go down by how many x's? 2 x's. Well, we found this change, and that is equivalent to 3 x's. What does x equal then? 0.004. Okay? Now, we can take this, and we can just stick it in there, and we don't have to worry. Was I supposed to divide by 3 and multiply by 2, or the other way around? It can get confusing. So then this is just 0.004. I didn't leave enough room there. And then this is going to be minus 2 times 0.004, which would be 0.008. So I get 0.079. Any questions? This one's trickier than the last one because everything had different coefficients, and so then the change is not as easy to just think about intuitively. So whichever one they're giving you the equilibrium information about, you can figure out that base change of x from that, because this change will be whatever this coefficient is times x. So we can figure out what x is. This change is going to be this coefficient times x, and this coefficient times x. Reactants go down, products go up. So Kc then equals, and again, we're going to write this out. We're not going to skip directly to the numbers. This is part of showing your work. And if you do everything perfectly all the time, then you could validly say you don't need to show your work. But who does that? I don't do that. Pretty sure you guys don't either. We all make mistakes. When we write stuff out and make a mistake, it's much faster to get the correct answer because we can go back and look at what we did, find the mistake and fix it instead of starting over and possibly just making the same mistake again. So now we plug our numbers in here. So we've got 0.004 times 0.012 cubed divided by 0.079 squared and that's a little number. Is that a good way to write that number? It's not a good way. Is that number correct? Yeah, I believe it is correct. But that number's hard to copy down, right? I got it on my calculator, and in order to be sure I got it on here correctly, I had to take my Apple pencil and count the zeros. 1, 2, 3, 4, 5. And then I had to count as I was doing this. 1, 2, 3, 4, 5. Is it easy to lose a zero there or gain a zero? Heck yes, right? So my kind of rule of thumb is if there's more than 3 zeros, we should put it in scientific notation. Personally, I can see 3. When it gets to be 4, they kind of start jumping around, right? So this in scientific notation would be 1.108 times 10 to the, right? And we're moving the decimal 1, 2, 3, 4, 5, 6 places. Is that a positive 6 or a negative 6? It's a negative 6. So that's something that students get mixed up on. So this is how I think about it. This is a small number, right? How does Mrs. K feel about small paychecks? Positive or negative? Negative, right? So this is a small number, the exponent is negative. If this is a big number, I feel positive about big paychecks, the exponent is positive. Your calculator can also do this for you, okay? On the 36X Pro, if you hit the mode button and you move the cursor down to the second line, it says norm sci eng. Move it over to sci for scientific notation, press enter, and then quit to get out of there. And then you think, oh dang, my number's gone. I have to do it all over again. This is no good. No, just press enter. It'll come back. And there it is. 1.107514821 times 10 to the minus 6. Okay? So we should probably report this as 1.1 times 10 to the minus 6. Equilibrium constant. Any questions? I'm giving you some of these kind of more basic concepts that you should have mastered in Chem 1A, but I'm not going to assume that everyone mastered them. So, I'm telling you to watch out for the multiplied things in the denominator. I'm telling you how to do scientific notation, right? I'm not going to do it again, but if you need help with that, please ask me, okay? 1.1 times 10 to the minus 6.